a number of journals in the sort of water area. And it's my pleasure to introduce one of our editors-in-chief for Journal of Water Process Engineering, Dr. Ludo Demy. He's going to give a brief overview of this webinar series and the two journals, and then he's going to introduce our speaker for today. We will also ask you to please put your questions in the chat, and they will be addressed after the presentation. Thank you very much. Go ahead, Ludo.
Thank you very much, Dawn, and thank you for Elsevier to host once again one of our joint desalination Journal of Water Process Engineering webinar. This is the second
recording in progress
webinar in January, presenting the winners of the 3-month thesis competition we have run last year. And today we are very privileged to have a high-level speaker from Ireland. That's the first time we have a speaker from Ireland, I believe. But before we get into the talk, I would like to give you a brief introduction onto both journals and some of the outreach activities we are doing to promote, obviously, great research being published in the journals, but also to support the community overall. Desalination, so we are also with Hong Sean today online with us. Sean is actually one of the co-editor-in-chief of Desalination with Professor Prof. Desalination, obviously, is a very well-established journal that has been publishing top research in the area of water desalination, but also other types of effluent industrial wastewater treatment. With a factor of 8.3, still very selective, was over 70% rejection rate overall. And the idea is that journal is really focused on desalination, while at GWPE we focus on non-desalination water treatment applications. And also, we look at emerging water production technologies such as atmospheric water generation, for instance, and other modeling processes that could be useful to develop case studies for industry and beyond. Overall. My co-editor-in-chief is Professor Chao Wong, who is not here today, or he's traveling. And we are also, welcoming submissions of virtual special issues, ideas, Now, in terms of outreach, we have obviously a presence on LinkedIn, so you can join our feed on LinkedIn, on WeChat, and on Twitter, where we promote activities, hot papers, sometimes also conferences or events happening. We started this webinar series just about 2 years ago, and I will give you a snapshot of that afterwards. And we started in 2024 a 3-month thesis speech competition that will be actually reinstated in 2025. So stay tuned, but probably in the next couple of months you will hear about this. We will call from PhD students to submit their applications by June. We also had a Trailblazer Award for mid-care researcher last year, where we gave, I think, 13 awards overall for emerging and established researchers in the water area. And like I said, we are always looking for people to support virtual special issues, so if you have a topic which have to match, obviously, our scope and be specific enough to target a specific hot area, we are very happy to discuss. So please feel free to email me about these ESIs. Now, the webinars we've been very fortunate to be supported by Elsevier for just over 2 years now, and we started in March 2023, short of 2 years, sorry. And we had speakers from literally any continent in a number of countries, talking about modeling, process development, materials development, as well as sensing, as you can see, as we had recently. So I guess the purpose of these webinars is to bring people together. We have been, very lucky also in terms of attendance. Several webinars had above 10,000 online attendees overall. So we're glad that you join us today. The 3-month thesis, like I said, will also be starting this year. So we're going to have another call for this competition in the next couple of months. So without further ado, I would like to thank you once again for joining this webinar. And now I would like to leave the floor to our speaker, Professor Xinmin Zhan from Ireland, who is going to let me share his slides now, if you want to try to share. And Professor Zhan will talk about complex but intriguing iron sulfide autotrophic denitrification. So thank you so much, Xinmin, the floor is yours.
Yeah, very much good. So is the slides okay?
Yes, thank you.
Very much. I just see whether it's moving or not.
Yes, very good. Thank you.
Good. Okay, very much. Yeah, thanks. Yeah, thanks, Lord and Verna for inviting me to join the webinar. So it's a great opportunity to share, some of the research I have done in the past 15 years, to the wide community. Very much. So just as a model introduced, my name is Xinmin Zhan. I'm a professor in civil engineering at University of Galway in Ireland. So before I start my presentation, I would like to use this opportunity to give a little bit introduction of my university. So the university is located in the city of Galway. It's a beautiful city on the west coast of Ireland. So university was founded in 1845. So you can see here, this is the original building. So at the time, there were only 6 students. So that's very spacious for the 6 students, studying and living in this building. And now the university has expanded from the old building to quite large. So you can see from to the left of this road, this over the campus. So the constructions are mainly in this corner, but then also beyond the photograph, there's quite a large area for sports facilities, for example, soccer pitch and hockey pitch and long tracks. So this green building is the engineering building. So the building beside a beautiful river, we call it Colorado River. So the river is among the shortest river in Europe, but it's very quite nice in summertime. So my office just I can see the river from my office window. Today I want to share some research about iron sulfide autotrophic denitrification. So we developed this idea around 50 years ago. So why we have this idea with that? We know that in most most wastewater plants they focus on organic matter removal, nitrogen removal, and phosphate removal. So the process is quite straightforward. So organic matter is removed by using autotrophic bacteria to oxidize organic matter, or we call it COD to carbon dioxide. And then nitrogen is removed through nitrophication first by oxidizing ammonia to nitrite, and then using autotrophic bacteria denitrifies, they reduce nitrate to nitrogen gas. And then phosphorus is removed from wastewater through the phosphorus accumulating organisms. So the phosphorus accumulating organisms, they uptake phosphorus from water to their bodies, and then phosphorus is removed. So this slide shows, a process based on these fundamentals for sodium removal, nitrogen removal, and phosphorus removal. Anaerobic announcing and also the process. So for this process, or even most of the first process based on these fundamentals, there are some problems. So one that because the oxygen is needed to oxidize COD and also for nitrification. So this is very high energy consumption. Of course, then was leading to the high operation cost. And also, organic matter or COD is also come to the site, so the energy stored in this organic matter will never be used. So there's no recovery of energy in the wastewater. And also, this process, they based on the autotrophic bacteria. For example, they use autotrophic bacteria to oxidize COD and for denitrification. So in this case, there's a high sludge reduction. Now this means that it will cause problem for the sludge treatment later. And also, for this process, it has been proven that they can successfully reduce nitrogen and phosphorus from wastewater, but sometimes it's still very difficult to get very low nitrogen and phosphorus concentration in the effluent. So if we move to the next slide, you can see here that I put the nitrogen and the phosphorus, I made a matrix of nitrogen and phosphorus requirement for the treating the wastewater. So if the nitrogen and phosphorus requirement was like nitrogen is about 9 milligrams per liter and phosphorus 0.3 milligrams per liter, then the biological nutrient removal process I introduced in the previous slide can work perfectly. But if the nitrogen requirement and the phosphorus requirement reduced to 3 milligrams per liter and 0.1 milligrams per liter respectively, then we have to use enhanced biological nutrient removal process, for example, post-denitrification process for removal nitrogen by adding organic matter, for example, methanol. But if we, in some kind of cases, there's a very strict requirement of very low nitrogen and phosphorus. For example, for the water, the water treatment plants they are built beside the sensitive water areas, the nitrogen requirement could, up to 2 milligrams per liter, and further about 0.03 milligrams per liter. In this case, biological nutrient removal process, we commonly used will be not very efficient. But in this case, I put as limit of technology scenario. In this case, we have to rely on some other technologies. In order to solve these problems, in around 2020, I am a researcher at the Galway, and we came out an idea we put as new green concept. So the idea of this, so for wastewater, with the organic matter, nitrogen and phosphorus, they will be treated through anaerobic process, for example, membrane bioreactor, anaerobic bioreactor. In this case, we can recover energy from the organic matter in wastewater by producing methane gas. And then the wastewater, they have ammonia and phosphate. And then we know that, because the COD organic matter has been removed, then it's very difficult for, it's difficult for traditional denitrification process and phosphorus removal process because they need the COD. So in this case, we have to rely on other non-traditional process. So for this wastewater with the ammonia and the phosphate, we can use a nitrifying filter to oxidize ammonia to nitrate or nitrite. And then the water contains oxidized nitrogen and phosphate, and use some ammonia. Then they go to the iron sulfide bioreactor. So in this iron sulfide bioreactor, the nitrogen can be removed, phosphorus also can be removed, or we also can be recovered. And then also the reactor also can achieve some emerging contaminant removal. So at the time, we proposed this idea. So based on some research we have done before. So, but in this new green concept, their core is iron sulfide bioreactor. So this bioreactor, they must achieve nitrogen removal, phosphate recovery, and emergence contaminant removal. Okay. So, the reason that iron sulfide bioreactor they can achieve nitrogen and phosphate removal is based on very simple mechanism, because some autotrophic denitrifiers they can use reduce the sulfur and iron, reduce iron or iron 2 as electron donors to reduce nitrogen gas. So, for example, in this biofilter, we add the iron sulfide material into the biofilter, and then we culture or enrich autotrophic denitrifiers on this material. Then we input the wastewater. So the wastewater, of course, because now we focus on nitrate and the phosphate, so the wastewater contains nitrate and phosphate. Then you can see this autotrophic denitrifiers, they will reduce nitrate to nitrogen gas. Okay, and then this is the chemical equation we can use to describe the autotrophic denitrification process. There are two electron donors. One is reduced sulfur, the other is reduced iron 2. Then you can see the sulfur will be oxidized to sulfate, and iron 2 will be oxidized to ferric. So with the ferric, for phosphorus or phosphate, the ferric can precipitate phosphate and form iron phosphate, and or the ferric can form the iron hydroxide material, then the phosphate can adsorb on this hydroxide material and then can be removed. Okay, so you see here that through this process we can external here two bursts. We can remove nitrate, we can remove phosphate. Okay. So based on this concept in around 2013, so when the refinery, when he was in my lab, so we started to test this with the natural iron sulfide materials. So there, on Earth, there are two major iron sulfide materials. One is pyrite, the other is pyrrhotite. So pyrite is like, they both are, very, they're widely found, but it's very difficult to find very pure pyrite and pyrrhotite. So luckily we got very pure, this material in China. So we tested, we brought to Ireland and tested in lab. So the pyrite can be emitted as a FeS2, and the pyrrhotite, depending on the contents of iron. Sometimes some pyrrhotite they have a relatively high iron content. So some pyrrhotite have relatively low iron content, but the X are close to 0. Okay, so sometimes we write as FeS. We represent the pyrrhotite. So we tested, we got this material from China, and then we crushed them in the lab, and then we put them into the filters and tested on 2 wastewater. So one wastewater is synthetic wastewater with nitrate is 28 milligram per liter, and phosphate is 6 milligram per liter. So we can see that we can get pretty good quality of the treatment. So the nitrate can reduce to 1.13 milligram per liter, and the phosphate reduced to 0.8 milligram per liter. And also we tested on the real, the actual municipal wastewater treatment plant, semi-effluent. So they have their total organic nitrate is 21 milligram per liter, and the phosphate is 2.6 milligram per liter. And then we got we treated their nitrate to 1.89 milligram per liter and P to 0.3 milligram per liter. So it's quite good efficiency. So you can see here that when we, for this two type wastewater, there was a high phosphate concentration, 6 milligram per liter or 2.6 milligram per liter. The reason was that because the type filter was so effective in removing phosphate. So so that's the reason we boosted, we add extra phosphorus into the wastewater to make the concentration high. So in case we can we can get some kind of idea of the removal efficiency. But the problem is the wastewater, when we run the filter, in order to get this good performance, the hydrogen time was at around about 24 hours. So of course, 24 hours sometimes we can use as a wet land system, but in order to make the process more promising, then we have to reduce hydrogen time. So then Dr. Yan Yang, then she studied practical research, and then she tried to figure out how to reduce the hydrogen retention time. So because when we use natural material, we noticed that they had a very low specific surface area. With this pyrite, that specific area was per gram 0.023 square meters. Then we think, okay, why not? We created some pores on the material to make the specific, to increase the surface area. So in the case, she made some micro pores structure on our material. So that this area not increase to 6 to 10 square meter gram. Okay, then we emphasize that when specific surface area is higher, then the bacteria they have more opportunities to use the material. Then we use this micro or nano structure inside material, and that we this slide shows data that we can reduce the hydrogen time to 3.6 or to even to 1 hour. So when we also treat the rear secondary means for effluent, so within total organic total oxide nitrogen is 11.3 milligram per liter, phosphate is 2.4 milligram per liter. So you can see that the total organic total oxide nitrogen concentration was always below 1 milligram per liter, and phosphorus concentration was always below 0.5 milligram per liter. But then, if you look at that, the wastewater had quite high phosphorus in the effluent. So if we use the phosphorus concentration, in the real wastewater, then the effluent here is very low. So this gives us an idea that we can reduce the size of iron sulfide, reduce the surface area of iron sulfide, then we can reduce the HRT and make the system more effective. So in the case Dr. Yang Bai, she continued the research in around COVID pandemic time. Then she used the synthetic iron sulfide. There are two reasons to use synthetic iron sulfide. So one is that when the iron sulfide was synthesized, then the particle size will be much smaller, then the specific area will be higher. But the other important reason, because that her research at the time was in the COVID pandemic, time. So in the case, we couldn't get a natural iron sulfide material from China. So in the case, we had to purchase, synthetic iron sulfide not available. So she used, she wanted to reduce the HRT. So in the case in her system, in her biofilter system, she mixed iron sulfide, synthetic iron sulfide, and elemental sulfur together. Okay, and then she treated synthetic wastewater. So you can see here, in the later stage, stage 4 and 5, 5 and 6, and the HRT was 1 hour, and she can got a very good, very low nitrogen penetration, okay, in the effluent when the operation was steady, and also very low phosphate penetration. So in this system, there are influent nitrate penetration was around 30 milligram per liter, and further penetration is around 3 milligram per liter. So the nitrogen loading rate is 960 milligram per liter per day. So the efficiency was very good. So you can see here that we can use iron sulfide system to remove nitrate and also to remove phosphate to very low level even in long-term operation. And as I described in slides in the previous slide when I talk about the NGO new green concept, also the system is very good at imagining contaminants removal. So Yang also did some research to look at how this iron sulfide can help can reduce the impacts of emerging contaminants on the autotrophic denitrifiers. So the left graph shows that she tested the nitrate reduction efficiency of the autotrophic denitrifiers on the different autocycling, concentrations. So you can see here when the recycling or TC, here when the penetration increases to 1 milligram per liter to 50 milligram per liter, then the nitrate reduction efficiency, the overall efficiency maybe was not impacted so much, but the nitrate removal kinetics was reduced significantly. Okay, when the recycling penetration was increased from 1 to 50 milligram per liter. But when the system had iron sulfide in the system, so you can see even when the recycling penetration is under 10 milligram per liter, there was no much difference to the nitrate reduction efficiency and the kinetics. So when the recycling penetration was 50 milligram per liter, there was a reduction kinetics was reduced a little bit, but the overall removal efficiency was the same. So this means that the system, the iron sulfide system, also can handle emerging contaminants, impacts for removal. So in case, okay, if we think that okay, we use smaller iron sulfides, then we can get we improve efficiency of nitrogen and phosphate removal of iron sulfide materials. Then we develop this idea that okay, why not we use iron sulfide nanomaterial, then we could achieve sustainable wastewater treatment, okay, by removing nitrogen and phosphorus, and also low sludge production, and also recover recoverable energy in the organic matter. So everything looks quite good. But then you continue work on by research, you have to study, and then we found something very interesting. So she set up 2 reactors, biofilters. So one built, both biofilters were filled with iron sulfide. So one filter, there was only iron sulfide, so there's no biomass, no autotrophic denitrifiers input. So in this case, we put as a biotip biofilter. But then the other biofilter, there was iron sulfide and autotrophic denitrifiers, we enrich it. So let's look at what's happening in the biotip biofilter. You can see here, we also, before we started experiment, we thought, we want to only use the biofilter as a control. So we didn't expect there was a nitrate reduction. But actually, you see that when the nitrate input concentration was 7 milligrams per liter, so there was a nitrate reduction, okay? And then you see there's even for total nitrogen was, in a biological reaction can be removed by 20%. And then, so we're interested to see, what happened to nitrate. Then you see here, there was not very low nitrite, but there was quite high content ammonia. Okay. So this means that, when the iron sulfide without biomass, the iron sulfide, synthetic iron sulfide can reduce the nitrate ammonia. But this happened, this hadn't happened before when we use natural iron sulfide material, pyrite or pyrite. So this is quite interesting. But then if we look at, what happened to the Earth before, when the Earth was formed, then we find that, this could something that we could link to what happened to the, when the life was formed on the Earth. So we know that when the life was, as soon as the Earth was formed, 4.6 billion years ago, so that the environment was very harsh, so there was no life. But the good is there was iron sulfide, material on the Earth. So there's no bacteria, but this iron sulfide material, can reduce nitrate to ammonia. But we know that ammonia is a very important part of the, formation of life, for producing proteins. So in case one of these kind of reactions will, is linked to the formation of life on Earth, it's very interesting. And also, if we, look at the biochemistry, that iron sulfide clusters are very essential to our cells because they are involved in electron transfer, and also they are very important, catalysts for our cells. So what does this mean between this, iron sulfide reduction of nitrate to ammonia to the formation of life? There's something that we should look at. But just say that, we young produce predator, then this is something very surprising to us because, we have worked on using natural iron sulfide many years, but we never noticed the reduction of nitrate to ammonia of iron sulfide. So then, then she continued with the research of the young graduate, and she noted that conversion of nitrite to ammonia only happens to synthetic iron sulfide. Okay, so she proved this. So she tested with iron sulfide, the synthetic iron sulfide. There's also this is synthetic FES2, and this synthetic FES, synthetic FES2, and then pilot plant. And then she used the experiment, with the dosage of 200 grams per liter. And so the dose is pretty high, just simulating what's happening in the biofilters. So you can see, for nitrate reduction only happened at 200 grams per liter FES, synthetic FES. And so the product was ammonia. So for FES2 and pyrrhotite, they didn't reduce nitrate to ammonia, so there was no ammonia at all. But in their system, there was quite a high concentration of sulfide, for FES2 system and a pyrrhotite system. The reason was that, on their surface, the sulfide, but the reduced sulfide was oxidized by sulfate because we didn't control the test environment to be, completely anaerobic. Then, we want to explain why. So because the only thing that we were afraid of that, because we bought synthetic iron sulfide, we didn't make in our lab, so we bought it, and then we were afraid that the iron sulfide, the synthetic iron sulfide could contain zero valence ion, because we know the zero valence ion will reduce nitric ammonia. So we're not sure whether the supplier used the zero valence ion to produce the synthetic FES, because we found the supplier didn't want to answer this question. They say this is their commercial, secret. So we didn't answer. But we are afraid that there might be zero valence ion. So we did a lot of testing. But SID showed that this was triolite. The synthetic FES was mainly triolite. So there was no zero valence ion present system, so very good. But we still said, okay, even we think that there was zero valence ion, and so we did a calculation, and from the mass balance result, at most the ion, the material we have, for 200 gram this material, it could be 46 gram zero valence ion. This, at most. And then we did a test, and we see that, even at the 46 gram per liter zero valence ion, so there was a reduction of nitrate, but not much. But then if we look at the system with 140 gram per liter iron sulfide and 46 gram per liter iron, zero valence ion, so there was not much difference of nitrate reduction ammonia compared with the 144 gram per liter iron sulfide. So in the case, we think that, okay, there was not much on iron. So then why the iron sulfide vapor reduction, but not FES2 and pyrrhotite? It is very interesting that we look at their surface of their material. So we know that on the surface of iron sulfide, there was the sulfur to iron ratio is 0.538. So you can see here from the chemical formula, there should be 1:1, but actually when we measure it by SPS, it's only 0.53. So in the case, there was kind of, so this means that on the surface there's a sulfur, deficiency on the system. So in the case, we think because of the sulfur vacance, it will plays a very important role for electron donation on the surface. So because of the sulfur vacance, so there might be production of this hydrogen radical because the electrons come from donor to the water and salt. So we use compound use the hydrobutanol to see whether the hydrogen radical play an important role. So she tried with different hydrobutanol concentrations. So you can see here, because the hydrobutanol can scavenge the hydrogen radical. So you can see with the different concentration of butanol, the nitrate concentration reduction is reduced. So this means that the hydrogen radical plays some critical role, but that the ion reduced by at most 15%. So this means that there were 85% reduction was caused by other reasons. Then we thought, okay, then there could possibility that the electrons can be transferred from the surface for the ion 2 on the surface. Then use the 2 and 2 prime PV as chemical. That this can chillate with ion 2 under iron sulfide surface to see whether this ion 2 on the surface directly donate electrons. So by adding different concentrations, we see that by using different concentrations of BPY, then the nitrate reduction, more efficiency, all the change a lot. So this means that the direct electron transfer on ion from ion to under material surface is very critical. So in the case, we emphasize the mechanism like this. This is because of self-awakeness. So there was a electron, localized electron donor. Then the water and also the nitrate adsorbed on this surface, and then this adsorbed hydrogen will reduce the nitrate to produce ammonia. So this result of our EST last year, so you'll be interested meeting because we also have produced some DBT calculation data there. I introduced that synthetic iron sulfide they can reduce nitrate to ammonia, but we noticed that in other reactor, so this is the reactor with the autotrophic denitrifies. So you can see here the nitrate also reduced, okay, and that's of course it's understandable. But then the product actually, in the beginning the ammonia concentration high, but then later on ammonia concentration is low. Okay, so this means that after we add biomass, the biomass actually they can change the chemical denitrification process. Okay, conversion of nitrate ammonia to a nitrate combined to the gaseous products. Okay, so the total nitrogen efficiency around 70–80%. Okay, and through the gas. So this is very interesting because as I say that in the beginning before the life were formed, okay, this ion the ammonia was very good for the formation of protein, so it's very essential for the life formation on Earth. But then too much ammonia will be very toxic. It will be toxic to the life. So the life, so just so clear like this, when the early stage in the life form, then the life they will change. They will gradually change the reduction of nitric ammonia pathway to the nitrogen gas. So this will show the resilience of the life to the ammonia concentration. So we'll say that the environment will influence life, and the life also transforms the environment. So this is very interesting phenomenon. I find this unsulfide filters are so complex but exciting. And also we know that in this reactor, look at the nitrogen, sulfur, and iron, they interact, their cycles interact each other. For nitrogen, you can see, almost every nitrogen species can be found in the reactor. From nitrate, ammonia, they form +5 to -3 valence, and also we have the sulfur same. The sulfur we can find this, reduced sulfide, polysulfide, sulfur, still sulfate, sulfide, and also intermediate. And for iron, iron can be, iron will be anodized to ferrous can anodize to ferric, but also ferric can reduce to ferrous. So it's a very complex system, but it's very interesting. And also, this on top of the data shows that the iron sulfide-based autotrophic denitrification also depending on the surface properties of different iron side material. So he tested iron sulfide and iron sulfide plus autotrophic denitrified biomass and pyrrolite and autotrophic denitrified biomass and X2 and biomass. So they look at. Then you see that all the systems can reduce nitrate, but for ABS mainly converted to ammonia. But when that biomass added, then there is no gas produced. Okay, but for pyrrolite is mainly, you can see for pyrrolite system, as I mentioned before, we never found out the conversion of nitrate to ammonia, so the nitrate reduction mainly go to the gas. Okay, so what's the problem? That's a very interesting part. So when I look at the surface iron and the sulfur composition on this material surface, and you can notice that for the synthetic iron sulfide, there's a sulfur weakness. But for pyrrolite, this iron weakness available. So because the sulfur weakness available, so in case it's good for chemical denitrification, but for pyrrolite, this iron weakness available, so it's good actually good for electron donation to the autotrophic denitrifiers. But for ABS2, there's on their surface, the iron and the sulfur are quite in a good balanced way. Then before my last two slides, I saw something very interesting also. So we know that when we use iron sulfide to reduce nitrate, then sulfur will be oxidized to sulfate. Okay, so because the electron will be moved from nitrate to sulfur, so it is sulfate. But the thing is, in the reactors in Yanyang, and we noticed that actually sulfate production is not as we expected. So, for example, in our reactor, she had 3 ports, on the reactor. So the first one around 3 centimeters from the inlet. The inlet, the wall is input from the water, and then there's 13 centimeters in the middle, and then there's around 34 centimeters from the top. So this the water is came out. So if we theoretically, according to the stoichiometrical equation, after we know that how much nitrate is reduced, then we calculate how much sulfate is produced. Through chemical equations. But that's not the case. So if we look at she tested the sulfate concentration along the theater column at different HRT. You can see here now we look at just one case, HRT 2.4 ounce. So you can see here in the bottom, the x-axis is the sulfate production, the difference between the sulfate concentration in the sample to the sulfate concentration in the instrument. So we use delta sulfate to show how much sulfate was produced. So you can see in the instrument the sulfate concentration, the delta sulfate was low, so this means not much going on. And then in the middle, the sulfate concentration for the sample rose. also quite, can be explained by, the reduction of nitrate. But, effluent, you can see the sulfide concentration actually was below the effluent with water. It's the darker sulfate is minus 20 milligrams per liter. So this means that, in the top, the sulfate produced in the middle actually was reduced. So at the time, because our shipping research in around 2017, so we didn't have the capacity to do a lot of economic analysis, but we suspect there was a sulfate reducing bacteria available. So when this phenomenon also, so when Yang did her PhD research, and then she did their quite good genomic analysis, and then she found this sulfate reducing bacteria in her system. So this proved that the system this reactor have the sulfate potassium bacteria, but also the sulfate reducing bacteria coexisting. So in case, for this iron sulfate reactor, then we can draw this graph. So you see, in the bottom, okay, we say the water is input from the, from the bottom. So in the first part, then the sulfate is called as the sulfate, okay, and the nitrate is reduced nitrogen gas, and then phosphate is removed through precipitation. But then in the other part, then the sulfate will be reduced to sulfate to sulfur again. So this sulfur then will be reduced by autotrophic denitrified as electron donors. And at the same time, the iron, the ferric ion can also be reduced to ferrous, and then the ferrous can also be used as electron donors for bacteria. Yeah. So you can see here, the system can achieve, can maintain a quite good sulfur cycle and ion cycle. So in case, we don't need to provide the ion sulfur material to the system continuously. Okay, so this is my slide, last slide. So my conclusion that chemical and chemical nitrogen transformations exist in ion sulfide filters. Complex nitrogen and ion and sulfur cycles are linked to complex functional molecular communities. So this reactor will provide a very good scenario for people who are interested to look at their material communities, how they interact with each other. And for a new green concept provides a solution for sustainable wastewater treatment. But also, I hope I need some research questions. I'm very interested, but I hope that some of the audience and people that are also interested in this. So one, this reactor that provides a good example for to look at the biological chemical cycles in our ecosystems. Okay, because the reactor has major chemical elements, nitrogen, sulfur, iron, phosphorus, carbon, and oxygen. So it's quite a good way to study, to use it to mimic the biological chemical cycles, in our environment. And also, how to link this, iron sulfide research in our reactor to look at the iron sulfide clusters biochemistry research, which are essential to our cells. Okay, this will be very interesting. Okay, so I would like to thank for the funding agencies, EUMER Korean project, Chinese Scholarly Council, Science Foundation Ireland, and Irish Research Council for help. And also, I would like to thank the researchers who have contributed to this slides. Professor Rehani, Professor Yang Hu, Dr. Yang Yang, Dr. Yang Bai, and Huang Huang, who here in her last stage of writing PhD thesis. And also my collaborators for the Galway colleagues in microbiology, Professor Zheng Hu and Professor Peter. Okay, thank you much.
Thank you very much, Xinmin. Very nice talk, very interesting. And I think it's very typical, especially in Australia, regarding resource discovery and polarization. We have a few questions already in the chat, so if you have any questions, please feel free to put them down. But I will start with the first question from Carabello Morantoa, who asks, how does adding iron sulfide affect the effluent water quality? Does it in any way change color to black or darker, given the precipitates being formed?
Yeah, that's quite good question. You know, in the lab research, we know that there was not black color. There was a kind of yellow color because there's fabric precipitate there. So, but this yellow color only happened, in their outlet. So it didn't impact the water quality. For the side research, Professor Yohani, he had done some, he had done some commercial study in China. So this didn't happen. So the color of the water is fine.
Okay, thank you. That's very clear. Second question. What are the drawbacks or limitations of denitrification with iron sulfides as used as electron donors? And maybe could you compare to other types of electron donors that would be, classical in the field, please?
Yeah, the commonly electron donors is like iron sulfide, ammonia and anomalous process. We use iron sulfide, and also some people, some research they look at, aluminum sulfur as electron donors. So for compared with anomalous process, is very efficient. But I think there are two drawbacks of anomalous process. One, anomalous process that is not suitable for low nitrogen, low concentration wastewater. The second is anomalous biomass is quite difficult to enrich and to maintain. But for iron sulfide, because iron sulfide is based on sulfide-based autotrophic denitrifies, for example, sulfide-based. So from our current knowledge that it's quite easy to get sulfide-based denitrifies, and even in the site, field research, it's very, the startup of the sulfide reaction is very quick. And also, there are material that technology can, conceal all types of wastewater, from low penetration or high penetration. For example, in our system, we use very low penetration, because we target the sanitary effluent from wastewater treatment plant. So in case, the ammonia penetration is low, always around, 10 milligram per liter, 10 milligram per liter, so there's no problem. The system is very efficient. And then compared to the sulfur, reduced sulfur as donor, reduced sulfur donor is very quick. Sometimes very quick and very efficient. But for reduced sulfur, there is a problem that it's very easy to get hydrogen sulfide gas. Because as I presented in my research, reduced sulfur is always not for sulfate, but no sulfate reduce. The system always has the sulfate reducing bacteria there, so they will reduce the sulfate to hydrogen sulfide gas. So But in unsulfide system, we never notice hydrogen gas production. The reason I guess that because hydrogen sulfide can be absorbed on this soil material. So and then bacteria can then use the hydrogen sulfide as like donor again. So I hope I can answer this question.
I think you answered some of the other questions at the same time regarding the presence of H2S as well, so you have covered that. The same gentleman is asking also if all the gases that were emitted were analyzed, especially also looking at NO3 and ammonia. Have you also analyzed that, and is that significant in terms of release, or how does it look like?
So, yeah, okay, I have answered hydrogen sulfide gas part.
I think you covered H2S.
Yeah, we analyze the N2O and nitrogen gas. Yeah, we analyze this, and N2O gas concentration was very low. It's ignorable. So mainly it's nitrogen gas. Yeah, we did the test.
Okay, very good. Then the last question is, where are the electron donors iron 2 and iron 3 from in your cycle? Do you use them, or you have like a second source, I guess?
That's really good. That's really good question. So that's really question. So for example, we noticed that sulfate is reduced to the sulfate is reduced to a sulfide by the sulfate reduced bacteria. So one electron donor is the carbon. You can see we never, the wastewater, internal wastewater didn't have organic carbon. No, the sodium was very low. So the sodium was around 20 milligram per liter. So BOD was very, very low. So, but because there was the bacteria around. So when the bacteria decay, then they produce, organic matter as electron donor. So this is one thing. But then another thing that, for example, like iron, there's a ferric in the system, but also there's ammonia in the system. So the ferric core also reacts with the ammonia, and this another thing. And also, I'm always thinking that the system is so complicated because there's so many elements, the cipher, the cipher can, we found a cipher from -2 to, +6. All this intermediate inside, so, and iron with +2 and +3. So maybe, I think that there's always some bacteria, they could use some intermediates as electron donors to reduce the other, elements. For example, reduce ferric to ferrous by using some intermediates, the sulfur intermediates. So, we're still working this, but the system is very complex. So, I couldn't get a clear answer, but there are some possibilities there. So.
Thank you so much. Let me see if we have any more questions. I think that's it. So I believe we are finished with the question time. So I would like to thank you once again, Xinmin Zhan, for your very nice talk, very interesting. The talk has been recorded. It's going to be put online on the Xinmin platform. So you can actually ask questions also to Professor Xinmin Zhan in the next few weeks. I think it's going to be open for at least a week or so. And thank you so much for joining. I think, Galway, if you want to do a closing?
Yes, sorry. If you hear noise in the background, there's drilling. But I'd just like to thank Professor Zhan for a very interesting talk today. Thank you very much for taking the time. All our attendees, thank you very much for joining us. And to Ludo for hosting today's session. And we hope to see many of you at our webinar next month. So thank you very much, everyone. Thank you. Bye.
Thank you very much. Yeah. Thank you for coming here, and also thanks for the audience. Thanks.
Thank you very much. Bye.
Thank you.
Recording stopped.